Hello, welcome to Inside Azure Innovations. This is where we pull back the curtain on what's powering Azure today, what's coming tomorrow, and even a glimpse of what feels like science fiction. Buckle up, we've got a lot to cover. Here's our roadmap for today. Data centers, servers, compute, networking, storage. Confidential computing. Each area represents a leap forward in scale, performance, and security. Azure's global footprint now includes over 400 data centers and 70+ regions, interconnected by hundreds of thousands of kilometers of fiber and subsea cable. This scale enables us to deliver reliable, high-performance cloud services worldwide. To support this scale, we're innovating in cooling technology. Microfluidics cooling moves beyond traditional cold plates, allowing liquid to flow directly across the silicon die. This dramatically reduces thermal resistance and enables denser, more efficient racks. Here's how it works. Microfluidic cooling systems use intricate channels and micropin-fin heat sinks to extract heat efficiently. Machine learning algorithms, inspired by biology, help design these systems for maximum performance. The result? GPUs running 20 degrees Celsius cooler, and the ability to push performance further. This isn't just theory, it's already in pilot production. Here's one of the first servers with in-chip microfluidic cooling, featuring etched cooling channels directly on the silicon. This breakthrough is expected to transform high-performance computing over the next 5 years. At the heart of Azure's server infrastructure is Azure Boost. By offloading storage and networking workloads from the CPU to dedicated silicon, we achieve higher performance and efficiency. This shift allows us to focus CPU resources on customer workloads. Here's Azure Boost, our custom offload card. It features high-speed Ethernet ports and a system-on-chip running Azure Linux, enabling staggering performance for storage and networking. Azure Boost delivers up to 20 GB per second remote storage, 36 GB per second local NVMe, and 400 GB per second networking per server. Security is enhanced with encrypted connections, and 100% of new servers, including AI and HPC, ship with Azure Boost. This enables bare metal GPU instances for partners like OpenAI, balancing openness with trust. Azure Boost also introduces Remote Direct Memory Access, RDMA, allowing virtual machines and GPUs to communicate with ultra-low latency. RDMA bypasses the networking stack, delivering consistent performance for demanding AI workloads. We've stretched RDMA not just across servers and data centers, but across entire regions. This enables multi-region AI training with reliable, high bandwidth, low latency communication, critical for scaling frontier models. Traditionally, Azure isolated untrusted containers using nested virtualization, which added performance overhead. Now, with direct virtualization, containers run directly on hardware alongside VMs, eliminating nested overhead and boosting performance. Direct virtualization supports live migration of parent workloads and their child containers. This means we can move entire workloads, including containers, across servers without downtime, laying the foundation for secure, high-performance multi-tenant computing. With direct virtualization, Azure container instances become first-class citizens. Containers can now access GPUs and InfiniBand networks directly, enabling better performance and more flexible resource allocation for AI and analytics workloads. Azure's networking has evolved with software-defined networking, SDN. Traditionally, network policy processing was performed in software on the host node, which could be resource-intensive for complex configurations. To address these challenges, we've introduced virtual network appliances, VNAs, like the Sirius platform. These appliances offload SDN policy evaluation to dedicated hardware, enabling horizontal scaling, accelerated traffic flows, and centralized policy management. Previously, network appliance workloads required dedicated VMs, which were compute-heavy and costly. Now, virtual network appliances apply policies at high bandwidth directly in hardware, saving compute resources and improving efficiency. Virtual network appliances are designed to handle massive bandwidth requirements and connect on-premises environments securely and at scale. For AI and ML workloads, model load times and checkpoint operations are significantly faster, supporting shorter training cycles and quicker iteration. With disaggregated SDN policy evaluation, for AI and ML workloads, time to train is critical. With VNet appliance, model load times are significantly reduced, and checkpoint operations during training are faster. This translates to shorter training cycles and quicker iteration for your teams. Beyond AI, VNet appliance improves efficiency for Azure services across the board. By offloading networking tasks to DPUs, you free up compute resources for what matters most, running applications and services efficiently without paying for unnecessary vCPU overhead. AI workloads demand enormous bandwidth and capacity. Training data, model checkpointing, and inference all require rapid access to storage. Every minute spent waiting for data means expensive GPUs sit idle, so efficient storage is critical. Azure's scaled storage accounts aggregate hundreds of petabytes and deliver many terabits per second of bandwidth. Architectural changes enable automatic scaling, so resources are matched to demand, eliminating manual sharding and accelerating both training and inference cycle. In a recent demo, we set up a cluster with 700 nodes and nearly 100 000 cores to generate massive read and write loads on a single scaled Azure storage account. Write throughput reached 22 terabits per second, and read throughput hit 51 terabits per second, enough to stream 2 million 4K videos simultaneously. This level of performance is essential for training trillion parameter models and orchestrating real-time inferencing pipelines. Security is foundational to Azure's infrastructure. Confidential computing protects data not just at rest and in transit, but also while it's in use. Hardware encrypted enclaves create a secure black box around code and data, with attestation capabilities for provable security. Trusted execution environments, TEEs, use hardware root of trust, memory isolation, and encryption to ensure that only verified code runs at startup. Data inside the TE stays confidential, and secure key management ensures keys are bound to hardware and can't be stolen or misused. Azure's confidential computing portfolio includes confidential containers, confidential VMs, secure enclaves for school, and confidential inferencing with Azure OpenAI Whisper. These services are generally available and support a wide range of workloads, from analytics to AI. Azure's hardware security architecture is built with 5 distinct technologies: confidential VMs, Silicon Root of Trust, Azure Boost, secure host hardware management, and Azure Integrated HSM. Security is anchored in hardware, forming a solid foundation for all layers of the stack. Azure Integrated HSM is now deployed in every new server, providing the highest standard of key protection. Keys never leave the hardware boundary, and all cryptographic operations are accelerated in hardware. Managed HSMs use attestation to prove authenticity, and keys are transmitted securely, never leaving a FIPS 143 boundary. Azure's signing transparency ledger records evidence of key management, software builds, and code policies, providing auditable proof of security and provenance. When a new key pair is requested, the hardware attestation is signed and logged in the ledger, allowing auditors to verify authenticity and integrity. In a glimpse of what's next, Microsoft Research has built the world's first analog optical computer for AI inference. Using light for computation, this technology promises up to 100x greater energy efficiency than GPUs, with no need for cooling and operation at light speed. The Cambridge team has built the world's first analog optical computer for accelerating AI inference. It's potentially 100x more energy efficient than GPUs and operates at room temperature, offering significant sustainability gains. Key components in the analog optical computer include projectors for multiplication, micro LEDs as the light source, and CMOS sensors for readout. These standard components are combined in novel ways to perform neural network computations using light. From microfluidics cooling and Azure Boost to direct virtualization, SDN offload, scaled storage, confidential computing, and optical AI, Azure is redefining what's possible in cloud infrastructure. The future of AI, scale, and trust is here, and Azure is leading the way. Thank you for joining this condensed journey through Azure's latest innovations. For more details, please watch the full session.